Today I'm gonna talk about how AMD and Hugging Face are collaborating, in the delivering the optimized LLM frameworks. That's what Hugging Face called a text generation inference, AKA a TGI. And I'm from AMD and AI group, and my name is Seungrok Jung. Since we don't have much time, I will just go straight to the details. First I will briefly talk about what kind of software and hardware do we have for the LLM inference. Okay, we're at the top, at the ecosystem and the toolkit. We do have a VLLM from UC Berkeley and another Hugging Face TGI text generation inference as our LLM inference software toolkits. That's a very super efficient, and it provides a very low latency and high throughput, LLM inference. That's why we chose that toolkit for LLM inference. Underneath the inference toolkit, we do have a PyTorch compatible, ROCm enablement, and same as for the TensorFlow, Jackson, and so on. And below that framework level, we do have a ROCm environment. We call it a ROCm libraries. That includes many BLAST library and convolution related MIOpen library as well. And also we do have compilers and other debugging profiling tools as well. And finally, we do have our high performance Instinct GPU devices and also the Radeon, the graphic card as well. So this is the latest MI300X GPU platform, which has 8 GPUs inside one server, and its aggregated memory capacity is 1.5 terabytes, which means that each one GPU unit has 192 gigabytes. And also in floating point 16 and brain floating point 16 data types, it provides 10.4 petaflops. And this number will be twice if the data type is floating point 8-bit. Okay, for speaking of the LLM inference challenges and optimization directions, the LLM workload is it needs special attention because its behavior is slightly not that typical, I would say, because for example, when we have some prompts. And after the prompt, we need to generate some tokens based on the prompts. In the case we need to process multiple different operations inside the model. For in general, a Llama type of model has this kind of architecture. When the input with multiple batches are they came to the model that will be embedded into a hidden state, and after that, all the processing will be usually matrix multiplication, and some of the softmax kind of a nonlinear operation as well. But finally, after the the front end the attention layer, the next one will be the linear layer as well. So majority of the operations are a linear operation, which is matrix multiplication, and also. Yeah, and also in case the when the model is huge and we have multiple devices, we have to process that model. We have to divide the model and to different to many GPUs. So once one operation is finished, we have to gather all the operations. That's what we call tensor parallel, and it needs all reduced operation between different GPUs. So this kind of all the operations needs special attention or special treatment. Otherwise the performance will be terrible even if you have very expensive GPUs. This is the typical a token processing view when we have a certain amount of the input prompt and the batch size. What we can find is that its behavior is quite different, between prefill phase and the decoding phase. Prefill phase is when we have all the necessary prompt tokens, so that all the tokens will be gathered together, and the workload volume will be very huge. So the matrix multiplication from the LLM model will be more like a very fat jam, meaning that all the dimensions are very huge, and which is usually a compute bound operation. So, but after the prefill operations, the LLM decoding is an autoregressive decoding procedure, which means that we cannot process a next token until the previous tokens are decoded. And the problem of the decoding phase is that it is the jam operations are very very tall and skinny, which means that it's an arithmetic intensity is very low, so that so it is totally memory bound, unless you have a really high batch size. So so in summary, the GPU should be very it should be very efficient in the compute bound prefill and memory bound decoding. So that's why we need a really high a very expensive GPUs with a very powerful computing power with a high memory bandwidth capacity. So these are the key key optimizations points that we AMD and Hugging Face are integrating in their Hugging Face TGI toolkit in terms of the LLM inference. So I'm gonna talk briefly one by one from the next page, but generally if you look at the typical LLM model, the flash attention that is optimizing the QKV kind of operations, and the page attention that that is for increasing the throughput for the when we use a KV caching scheme, and gem operation for a PyTorch tunable ops for much a higher efficient HIPLAS LT from AMD, and HIPLAS and recall and quantization. Or I'm gonna talk one by one from next slide. Okay, flash attention. I guess everyone, every LLM backends are relying on this flash attention module, because if you look at the attention, it's not that operation friendly, meaning that you will have to have a softmax nonlinear operation right after a QK, a query and key matrix multiplication, which is not that ideal for GPU operations. What the flash attention does is that it just tiles a tiny bit of the query, and it processes the partial outcome one by one, so that the partial outcome will stay more in the GPU cache instead of the HBM, because definitely GPU SRAM bandwidth is much higher than HBM bandwidth. And also another advantage of using flash attention is that we can pipeline the matrix multiplication and softmax, so that we can we can reduce the total number of the latency as well. So but the question is how can we use this kind of fancy algorithm on AMD environment? It's quite in fact it is quite simple, because we put much effort enabling this this kind of high performance kernels in the ROCm GitHub. So in the ROCm GitHub, github.com ROCm.flash attention, that's one of the choice that people can just quickly clone the repo and just run it on the AMD device. We do have another one more flash attention, which is based on the OpenAI Triton kernel language, but it's not here. But if you look at the ROCm GitHub, then you easily find two different flash attentions. The much more easier way would be you can just utilize out of the box from the Hugging Face transformer libraries, because we already integrated everything in the transformer libraries. So in the transformer library API, once you just specify flash attention 2, then it will automatically run everything in the flash attention algorithm And the last one will be like you can just simply install like VLLM or Hugging Face TGI. That will be like another like an out of the box experience that people can utilize flash attention. Okay, paged attention, like this one became increasingly more important because like okay, model is like bigger, but the problem is that recent model has like very long, it supports like very long sequence length. Like old model supports like a 2K, total token length, but the Llama 3.1 they started to support 128, kilo K, inputs, which means that once you start to decode the LLM models, and all the like memory capacity will be occupied by the like a KV cache, not the model. Yeah, model is huge, but compared to the KV cache is exploding. So that's why we have to use like a smart way of like treating KV cache. So what page attention is doing is that instead of using the contiguous memory space in the HBM, because like for like like 8K tokens or like 128 8K tokens, you cannot save, you cannot store all the like cache in the memory because you will easily be out of the memory. So what it does is that instead of using the contiguous memory, it splits the like a KV cache into like small pieces of the block, so that it uses like a what do we call like a block page table. So it has like a virtual page attention and like a physical page attention table mapping, and one of the like a key benefits is that it can prevent the like memory fragmentation that happens from the contiguous memory occupation of the KV cache. So that's why like we are like highly relying on this paged attention algorithm. But yeah, good thing is that it's already like implemented in like TGI and VLLM. So once you download it, like everything is already it should be like out of the box. PyTorch tunable, this could be like more like exclusive to the like a ROCm environment, because usually like when you run like matrix multiplication in PyTorch, inside the PyTorch you will have a like a heuristic algorithm that pick up the like best performing gem out of the ROC+ library or HEAP+ library. But the problem is that sometimes generally it's not the optimal performance. It's installed in your like a Docker environment. So yeah, PyTorch tunable like it has like first like it profiles the workload and it stores like a best performing gem. Like it could be like from ROC+, could be like a HEAP+ or HEAP+LT. So it records the best performing gem in a table. So during the runtime, it pick up the like only the like best performing gems from the table. That's why it always like guarantees you to have the best performing gem operation, because like LLM is highly depending on gem. So yeah, PyTorch like a tunable, yeah, you will easily get like a much higher like a performance boost. And good thing is that like yeah, same as the other techniques, we implemented everything in PyTorch. So once you just download the like a latest like a nightly or like a stable version of the PyTorch, once you just set that environment variable PyTorch tunable enabled, then it's just out of the box. It will behave like this way. It will pick up the best performing gem in your Docker image. So heap graph, this is like very similar to the like a CUDA graph. The one of the like a key disadvantage of the like GPU operation is that like when the when the volume of the job is like very small, then CPU could be a bottleneck, because like all the like a kernel launching will be from the CPU. But once the CPU is like really busy for like a kernel launching, the GPU has to be idle because it is just keep waiting from the like a command from the CPU. So yeah, okay, prefill is okay because the volume of the job is like quite like high. So yeah, CPU just like it is not necessarily to launch the kernel frequently, but decoding is a problem because decoding is like a very like it's like a autoregressive, like decoding is like super fast. So yeah, the CPU cannot handle all the kernel launching for multiple GPUs at the same time. So what heap graph does is that it's same. It's it profiles a workload before the actual inference. What it profiles is that it stores the many operations into a small, not small, it's just one single a single graph, so that CPU can just launch just one single kernel to the GPU, and after that a GPU will handle multiple operations from the aggregated one single single graph. So this is a super performance boosting for decoding, and also in the multiple GPU scenarios. I guess this could be the last one. Quantization. Many ML communities and research centers, they have many very smart ideas about how to how they can effectively quantize the parameters and quantize the activations. Well, speaking of the activation and parameter quantization, from commercial direction could be floating point 8-bit native support, but in case when we care about memory bandwidth, for example, when we have insufficient HBM memory, then what we can think of is that utilizing the this 4-bit type of weight only compression that is provided from GPTQ and AWQ, and what it does is that it just compress the data from a 2-byte format into a half byte in the memory, and during the run inference, it just on the fly reconvert back to the floating point 16 or BF16. So the computation is still in floating point 16 operation, but it still has a huge benefit for saving the memory bandwidth and also a memory capacity as well. Or if the usage is quite, there are many multiple works on about how to enable these techniques on NVIDIA GPU and AMD GPUs, but everything every library is upstream by now. So in case of GPTQ and AWQ, we do have the transformer library compatible libraries are ready, so you can just clone those libraries, and you can just run on top of the AMD GPUs out of the box. And also, those are recently integrated into native a transformer library as well. So you can, if you just configure the AWQ config or to a GPTQ config, then it will automatically use the AWQ or GPTQ kernels underneath. The last one is that we can just simply utilize VLLM and TGI, because everything is integrated right now. Okay, commercial LLM serving. The TGI from Hugging Face could be one of the best choice if you are considering the commercial deployment, because we already, AMD and Hugging Face, we collaborated for a while. We enabled all the high performance kernels into the TGI. So and also you can easily find the latest Docker file. So once you just clone the Docker file, and that's it. Everything will be, every high performance libraries are already integrated, so you don't have to worry about anything. And the other thing is that in the VLLM this is not from Hugging Face, but this is another LLM toolkit that we are heavily relying on, because this one is also very super efficient for a high throughput high batching scenario. So from AMD we prepared many collaterals that people can utilize these toolkits. So recently we just published some ROCm VLLM Docker on the far right. That one should give you the really high performance high performance VLLM inference throughput and latency. So where I hope people try that out and get like what is the like the latest like performance that we are providing. Okay, back to the like TGI from Hugging Face again. The like optimizations that I talked for a while. They are all already like integrated inside the like TGI, attention, jam, page heavy caching, and recall quantization and heap velocity. So if you just like clone the clone the like a TGI and clone the model, then everything will run out of the box. Okay, I think I have like 4 minutes, and this is the one that this is the like a demo that I prepared before I came here. This is the Llama 3.1 like 4-5 billion model running on 8 GPUs. Maybe I guess somebody has to press the enter. Just give me a second. Oh, sorry. Can you press the enter? This is a video clip, so. Oh.
We focus in the term window and press enter, or how?
Oh, this is the like video clip embedded in the slide. So yeah, there should be a play button at the bottom. Oh, sorry.
So it's not in the upload.
Not uploaded? Oh, okay. Or maybe I should like explain instead. Okay, what had happened is that this video clip, like what it does is that you can launch a TGI from Docker command, and after that it will automatically load the 4-5 billion from Llama 3.1, which is like about like 90-10, no more than like 800 gigabytes, and those like 800 gigabytes will be split across like 8 GPUs. And it will, process the like a token processing for the prefill and decoding. So, well, unfortunately, due to the like technical like some issues, it does not. We couldn't play here right now. But anyway, like, everything is ready. So what is that you can just clone the like a TGI Docker file, and that's it. Like everything is already implemented here. So yeah, Llama 3.1 and everything will be run out of the box. Okay, lastly, like we prepared like many things for the like end users, because like I still believe that like ML is more about like participation from ML researcher and from many startup and many research center as well. So we provide like many like fundamental libraries that people can utilize. For example, where we have like a PyTorch like upstream for like stable version and the nightly, and many different like Docker-based Docker that ROCm libraries are pre-installed. Oh, can you press the enter? I couldn't go to the next slide. Oh, yeah, okay. And also, like we do have like we want to share our like stories about like how we accelerate like multiple workloads on our like ROCm environment. So we prepared like a ROCm blog and a AMD community AI blog as well. So, and also we have like many collaboration articles that that has like all the details that how we achieved the like a higher performance, like an LLM optimization through the ROCm Hugging Face and Optimum and Hugging Face MI300 AMD blog as well. And lastly, those are the like fundamental ROCm key libraries. So I hope like people just try them out, and I hope that people participate in and optimizing those like key libraries, so that we will have like more like user base in this like area. I think thank you for like attending like this session, and I hope I give like any like yeah tiny bit of like information to you, and thank you so much.